So as I mentioned in the introduction video, we're going to be looking at how calculus continues to develop. We're going to concentrate mostly on the computational aspects of it, though at this time there were also things going on to sort of bolster the theoretical underpinnings and things like that. We will talk about some more theoretical things as well, but I'm going to spend most of the time discussing how this new language of differentials was used. It was used to both describe problems, describe physical situations, and that sort of thing, and then the methods that were used for solving these differential equations. Okay, so these equations that we're going to come up with are going to be equations involving differentials. So they are differential equations. So remember what this says. We have variables, x, y, s, t, whatever they're called, that are somehow related to each other. We're not necessarily, saying that one happens to be an independent variable, though we will often, assume that one of them is sort of the independent variable. Okay, but we've got differentials, and what this does is it doesn't say how one variable relates to another variable. It says how the changes of one variable relate to the changes in another variable. More precisely, it says how the infinitesimal changes in one variable relate to the infinitesimal changes of another variable. And so then by adding up all of these changes, that is, integrating, we can figure out, we can get a relationship, a more concrete relationship between the two variables. Okay, so some of the things that we're going to be talking about throughout this week, mostly just the videos that I make today, are what are cosine and sine. I mean, we know what cosine and sine are in terms of trig functions, but is there a better analytic way to think about them? That we'll get to a little bit later. If we describe a situation using the language of differentials and infinitesimals, how can we find the function that describes that situation? That's what I was just talking about. Given relationships between differentials, how can we get to the relationship between the variables themselves? Then we're also going to be continuing our transition from just curves and things like that to the notion and the language of function. Okay, so the first thing that I want to talk about are some of the developments that we have in calculus techniques. When I say calculus techniques here, I don't mean, let me move that cursor. I mean basically two things, or at least two things. One is using calculus. Again, when I say calculus, I mean the language of differentials, infinitesimals, all of this sort of thing, to describe problems, and then the methods that we have for solving these differential equations. So I'm going to talk about this first problem. First, the catenary problem. This was posed by Jacob Bernoulli. Now, the Bernoulli family was a very influential mathematical family. We're going to talk about three of them today: Jacob, Johann, and Daniel. Jacob and Johann were brothers. So here's a question that Jacob posed. It says, let's say we have, it says a flexible, the book uses the term flexible but inelastic rod. You can also think in terms of chains and this sort of thing. Just a string, not a rubber band because we don't want it to stretch or anything like that, but an inelastic but flexible thing. Okay, and this is what we're talking about is often sometimes called the chain equation because it models a hanging chain. Okay, so let's say we've got 2 points here. Let's call this point A, and let's call this point B. Oftentimes A and B will be at the same height, but they don't have to be. Here B is just a little bit lower than A. And I'm going to keep it like that. No, I'm going to move B over a little bit just to make full use of the available space. So we're going to have that. And then we have a chain hanging between them. And we want to find the equation of this chain, and we want it to be like in the form y equals f of x. Okay, and just sort of general considerations show us that it will be the graph of a function. In other words, it's going to pass the vertical line test. It's not like the chain is going to sort of sweep back over itself and then go over like that. Okay, so we want to get this in the form y equals f of x. So Bernoulli developed a solution, and he starts with this differential equation, which says that dy is equal to s over a dx, or the way that I have it written in the slides, dy dx is equal to s. Excuse me, is equal to f is equal to s over a. Okay, well, let's think about where this comes from. I'm going to erase this, but let's think about where this comes from. So there are two considerations that we're going to look at, and I'm actually going to make this chain. I'm going to make the droop a little bit more dramatic, so I can kind of draw better pictures. So we're going to have something that looks like this, okay? And the chain has even density. That's going to be very important. And we're going to call this point right here, that's like the vertex of this point, that's the lowest point. We're going to call this 0, 0. That's the origin, x equals 0, y is equal to 0. And I'm going to analyze both sides of the chain. I'm really going to only analyze the right side of the chain, and the same thing will apply to the left side of the chain. So let's say this is kind of like the x-axis going this way. This is the y-axis. And let's take this point right here. It's a generic point on the chain. We're going to call this xy. And we want to think about the tension in the chain at this point. We want to think about the tension in the chain at this point. Now, it's going to be parallel to the tangent of the chain. Okay, so let's notice a couple of things. By assumption, I didn't say this explicitly, but by assumption, the chain is hanging still. It's neither moving up, nor down, nor left, nor right. So all of the forces have to equate. They're all equal in magnitude. So let's think about the tangent, or the horizontal force. So let's say if we look at something like this, this is going to be the horizontal tension, and it has to match exactly with the horizontal tension here. So like this. Like those two things have to equal to each other. Well, let's say the tension down here, or the magnitude of the tension down here in the x direction, I'm going to call it T of 0. Well, this has to equal whatever the vertical component is of this tension. So if you call this theta, it's going to be equal to the magnitude of T of x times cosine theta. Okay, but we can also consider the differential triangle, in which case this is dx, this right here would be ds, and this is dy. And then so cosine theta is going to be equal to dx over ds. Okay, so what we get then is that dx, so if we solve this for dx, we can get an expression for dx. Dx is equal to that divided by that times ds. Okay, so you can just write this down and solve for dx on your own. Now, what about in the y direction? Well, if you look at this length of chain, right here, what are the forces acting on it? Well, we're going to have the vertical component of the tension. So similarly, this is going to be equal to the magnitude of Tx times sine of y, which is dy over ds. And if we just, again, look at this portion of the chain right there, there's two vertical forces acting on it, the weight of the chain and the tension of the chain pointing in the up direction. Because notice right here, at this point, there's no vertical component of the tension here. Okay, so there are two forces acting on this segment of the chain: the tension pulling it up this way, and then the gravity pulling it down. Well, let's assume that the chain has uniform weight. If the chain has uniform weight, then the weight of the chain from here to here is just going to be equal to rho times s. Where I didn't say it explicitly, but s is the arc length of the chain. So the distance from there to there, the x direction is x, but the length of the chain is going to be equal to s. Okay, so notice what this tells us. Notice what this shows us that we can do. We can solve this for dx, we can solve this for dy, and then divide them. So if we solve this for dy and we solve this for dx, what we get is the following. We get dy dx is equal to rho, which is the weight density of the chain, times the magnitude of the tension at 0, times s. That looks like a backwards 2. I can never write a backwards 2 when I need to. Not that comes up a whole lot in my life. But this is what we have here. And then so the a in the differential equation, dy dx equals s over a is just equal to this, but put in the denominator. I'm not sure why it's written as s over a instead of a times s, but that seems to be the common way of doing things. Okay, so now we haven't exactly solved this problem yet, but what we have done is we've gotten a differential equation that helps us. So we've gotten the differential equation dy equals s over a dx. Now, there are a number of ways to proceed at this point. I'm going to give you one of them. So we can use the relationship ds squared is equal to dx squared plus dy squared. And if we solve this for dx in terms of dy, we get that dx squared is equal to a squared over s squared times dy squared. And so dx squared is going to be equal to a squared dy squared, and I want to get a common denominator, so we're going to get s squared y squared divided by s squared. I forgot the dy squared. Okay, so this is one way that we can do this. And then another thing that we can do here is we can factor out the dy squared and solve for dy. And now what we're going to get is dy is equal to s over the square root of a squared plus s squared ds. Now, this is definitely something that we know how to integrate because we can just use the use stuff. Now, one that's a little more challenging is we can also get an equation for dx. And the equation, using similar methods, the equation that we're going to get for dx will be a little more challenging to integrate. So we're going to get dx is equal to a dy divided by the square root of y squared minus a squared. Okay, now we actually know how to solve this now. This is going to be a trig sub. We're going to say that y is equal to something like a secant theta, and then we'll be able to solve it that way. I have a note. There was something else that I wanted to mention that I forgot, and so I'm going to look at this really quickly. Yeah, so I want to mention another way that we can think about this, beginning with this equation here. I'm going to get a different sort of differential equation. Okay, so we've got dy is equal to s over a dx. Now, what we can do here is essentially just like differentiate this again. And when we do that, we're going to get d squared y. I'm going to have 1 over a. And remember, we have to use the product rule here. So we're going to get ds dx plus dx squared. Now, dx squared here is going to be equal to 0, but why can we say it's equal to 0 here? When we're thinking about x, one of the reasons that we can say this is we're thinking about x as being the independent variable. So dx is fixed, so then dx, sorry, this is not dx squared, this is, I messed this part up. This is s times d squared x, s times d squared x. So this is not showing up all the way, so let me move things to the left a little bit, to the left, to the left. So we're going to have dy squared. Again, we need to use the product rule here. So we're going to have ds dx plus s d squared x. And again, we're thinking about x as being the independent variable, so dx is fixed. It's like, 1. So then if we d that again, it's going to be equal to 0. And so in general, anytime you do something like this, you're going to get 0 for the independent variable like this. So now what this gives us is this is equal to 1 over a times ds times dx. But what is ds? ds is the square root of dx squared plus dy squared, and we're multiplying this by dx. And now I can factor out a dx squared, and when I factor out a dx squared, I'm going to get 1 plus, well, if I factor out a dx squared here, I got to divide by dx squared, right? So it's going to be dy over dx, that whole thing squared. So that's just going to be y prime squared. And then the dx squared comes out of the square root as a dx. So I'm going to get dx times dx. And now when I divide both sides by dx squared, I made a mistake here. Sorry, that's d squared y is what I'm doing here. I'm going to get d squared y over dx dx. This is just the second derivative is equal to 1 over a times the square root of 1 plus y prime squared. Now, one of the reasons I want to mention this, in addition to just kind of giving another way of writing this differential equation, I'm going to rewrite it up here. So notice, by the way, I'm using Newton's prime notation here because I believe that it's convenient. So we're going to have y double prime is equal to 1 over a times 1 plus y prime squared. Now, what we're going to do here is we're going to introduce a new variable. I'm going to call it v. V is going to be equal to y prime. And now we can write this equation. On the left-hand side, I'm going to switch back to Leibniz notation, dv dx. And on the right-hand side, this is equal to 1 over a times the square root of 1 plus v squared. Now, this is a separable equation, and as I mentioned here, this is something that Leibniz was able to solve. Okay, now I don't know if they got it to this point or not. This is not apparently how the Bernoullis solved it, but this is definitely a way that we can solve this. We can solve this for v. Once we solve this for v, that's going to give us y prime, and we can anti-differentiate that to figure out what y is. Okay, so that's just another alternative way of thinking about this. This sort of mixes a few notions here that we have together. Okay, so this was the solution to the catenary problem, and as you can see, it relied on calculus both to formulate the problem in terms of differentials, that is, to find a differential equation that the curve of the catenary satisfies, and then of course you have to use calculus to be able to solve this as well. And you can see that there's a very algebraic thing going on, where we're sort of on the one hand, when we think about calculus, we think about, we're looking at functions and analysis and epsilons and deltas and stuff like that. But really what we're doing here is a mix of sort of that, but also just these algebraic manipulation, these algebraic rules, treating these differentials as algebraic objects that kind of have their own rules that are very similar to things that we're used to, but also have some differences as well. So again, just to reiterate, in 1691, Leibniz solves this separable equation. It's exactly what we have here, or so this is a form of it, and he sort of introduced this technique to solve the dy equals f of y over x dx via making substitutions. And Euler also came up with a class of equations that you could make various substitutions. And if you take a differential equations class, you'll see more of those as well, or different of those equations different types of equations where you can make substitutions and transform them into an equation that you can solve. Okay. Moving on, we have this problem. I think this video I've gone on long enough, so I think I'm going to wait until another video to talk about this problem, the brachistochrone problem. This is going to be similar to the catenary problem. If you have a point A and a point B, you want to find the path that connects those 2 points that is going to give you the shortest distance traveled by an object going down that path. And as we will see, this is also going to give you something called, this is also going to give you a solution to something called the isochrone problem. Anyways, we'll do that in the next video.